Okay, welcome back everyone. We are still discussing various coordinate systems in Schwarzschild space-time. And the most important one, which I spent most time with, of the ones we have discussed until now, were the Eddington-Finkelstein coordinates, which are, I think, the best coordinates for understanding what's going on at the horizon. So, because you see the light cones in these coordinates very nicely, and this gives you a good idea why the horizon is called a horizon. Today I want to begin with another coordinate system, which is also, in my view, quite instructive and quite interesting. It's not so often treated in the standard textbooks, although I think it's also very helpful for understanding some features of the Schwarzschild spacetime, in particular if you're interested in collapsing objects and the process of how something collapses and goes through the horizon. Then these coordinates are very useful, and they are called Perlick-Gülstrand coordinates. I will spend some time with this. And then the last ones I will mention are the so-called Lemaitre coordinates. This will then be again fairly short. But let's spend some time with the Perlick-Gülstrand. Well, you can introduce them in various ways. I think the quickest way, which leads you on the shortest path towards the result, is the following: that we want to find a coordinate transformation We begin again with our standard Schwarzschild coordinates, Tr, theta, phi. These are always my notations for the standard Schwarzschild coordinates. And as in the Eddington-Finkelstein case, we only transform the time. This time I call the new time T bar, R theta phi. And the goal is, in such a way, to do the transformation in such a way that the hypersurfaces T bar equal constant. So these are the instantaneous snapshots of the space-time, so to speak. Yeah, you fix the time and you look at the space at this fixed time. And if you do it in these coordinates, then what we want to have, that this is flat. And surprisingly enough, that's possible. Yeah? So if you remember the isotropic coordinates, there we were able to find a coordinate system for Schwarzschild such that these hypersurfaces, in this case where they're called T equal constant, that they became conformally flat. Yeah? The standard Euclidean metric, but there was still a factor in front of it. Then the angles are preserved in comparison to the flat metric, but the lengths are not. Actually, it is possible to find solutions where both angles and lengths are preserved, and these are the Perlick-Gülstrand coordinates. So let's see how we do this. So the ansatz for the metric, for the transformation, so I only transform the time coordinate, and I try it in the following form. Let's just see if it works. I want to try it in the form that T bar is just T plus a function of R alone. That's my ansatz. Let's try if this works. If it would not work, we would have to try something else, but it does work. So then we have to insert this into our metric. So first of all, we also need, of course, differentials. So dt bar is then dt plus f prime of r dr. And we want to replace the dt in the metric. So we have to solve this equation for dt and then insert this into the metric. And what was a metric? Hope everybody remembers the Schwarzschild metric. Minus 1 minus rs over r, c squared dt squared, plus dr squared over 1 minus rs over r. And for the angular part, I write, as I did already last time, r squared, the omega squared. So this is, just to remind you, this is d theta squared plus sine squared theta d phi squared. Okay, and we substitute for the dt, right? We solve this for dt and substitute it into this expression, and then we get the Schwarzschild metric and the new coordinates. So we get G is minus 1 minus Rs over R. And now comes the dt squared, c squared first. C squared. And for dt, I write this expression. So this is dt bar minus f prime of r dr. This is dt bar minus f prime of r dr. And the rest I just copy. I don't change the r. I stick with my old radius coordinate r in this case. Okay, I'm afraid I have to multiply this out. And this minus 1 minus Rs over R, c squared. And now I get dt bar squared. And the mixed term, and again I use this shorthand notation, where I just write dt bar dr. And I remind you again, this means the symmetrized tensor product. Yeah? Tensor product is not symmetric. So if I would write the tensor product sign here, then it would be wrong. Yeah? If I put the sign in there, then I have to write it as 1/2 this, plus 1/2 the other way around. And my convention is that if I omit the tensor product sign, then I mean the symmetrized version. And the last term is f prime of r squared, dr squared. This bracket is closed, and the rest is still what it was. Plus r squared, d omega squared. So we see, well, the price we have to pay is we get a mixed term. Yeah? And actually this is unavoidable if you want to find something which is spatially flat. So we get a dt squared term, and then we get a mixed term. We have 2 times the minus sign. So it's plus 2 times f prime 1 minus Rs over R dt bar dr, and then we have 2 terms with dr squared. So let me begin with this term. There we have in front of the dr squared 1 over 1 minus Rs over R, and then we get this term here. This is minus f prime of r squared times 1 minus Rs over R dr squared plus r squared d omega squared. And now I can see what my f prime should do for me. I want to have the spatial part flat. So this is supposed to be just dr squared plus r squared d omega squared. So what we want to find is a function f such that this here becomes 1. Then we have just a flat metric. Yeah? So if in this if we succeed in doing this, then we have the surfaces t bar equal constant. The surfaces t bar equal constant. For this is irrelevant, this is irrelevant, only this is a metric on these surfaces. And then it would be the flat metric. So what is f prime? So I write it slowly, can't do this in my head. So this is minus f prime of r squared 1 minus Rs over R is supposed to be 1. That's what we want to get. And then we have to solve for f prime. Let me see, I think I multiply with this denominator. Then I have 1 minus prime of r squared, and then this thing squared, right? Is over r squared, and this is multiplied to the other side. So I have 1 minus Rs over R. That's not, is it plus? Yes, yes. So these 2 terms cancel. And if I take the square root, I get f prime of r. I think now I can do it in my head. Root of Rs over R divided by 1 minus Rs over R. Okay? Well, actually I get, of course, either the positive or the negative square root. I will choose the positive sign. And I will discuss later what happens if we had chosen the minus sign. So let's choose the plus sign. So what is usually called the Perlick-Gülstan coordinates is the one with the plus sign. The other ones would call time-inverted Perlick-Gülstan coordinates or something like that. Okay, and so we have found our f prime. What was the f prime? Here is the equation. The f prime relates the differentials of the coordinates. So let's copy this again. So this means that dt bar must be dt. And now plus f prime, I copy this from here, plus root rs over r 1 over 1 minus rs over r dr. And actually, this can even be integrated, so we can even write down the t bar explicitly. So if I put integral signs in front of everything, I get here an elementary integral. And what I get is the following. That's something with a log. Oops. So where am I here? So this is t plus 2 over c root rsr minus rs over c, and then comes the log root r plus root rs divided by root r minus root rs. That's it. Up to an integration constant, which is irrelevant. You want to find just one transformation, right? You can shift your coordinates, of course, with a constant as you like. So that's the result. So we have found the transformation which makes this expression here equal to 1, and then we have a flat spatial part. So let me write down the metric in these coordinates, and this is what we call the Perley-Gülstan. The Schwarzschild metric in Perley-Gülstan coordinates. Oops. So this is Schwarzschild metric. So I have G is minus Rs over R C squared bar squared. Then I have the mixed term. And here I have now to insert my f prime, which I have calculated down there. So I get plus 2 times f prime. Here's f prime. And we choose the plus sign. So it's root Rs over R. Then what? The 1 minus Rs over R in the denominator, and then I continue here. Now comes, that's very nice, the 1 minus Rs over R in the numerator, d t bar dr, and then comes the flat metric, the flat 3 metric, dr squared, oops, r squared, d omega squared. And yeah, this goes away, of course. And that's it. So you see the price we have to pay is a mixed term. It doesn't work without a mixed term. You can try to do it without a mixed term. You will not get the spatial part exactly flat. You can get it conformally flat. Is there a question?
No, we just saw the third line on the missing C's, I think so.
Oh, yeah, that's very likely. Okay. So where's the C missing? Let me check.
One big bracket.
Big bracket. Where's the big bracket? Here? Did I forget this? Yeah. That's very likely. Okay, it's here, right? Yeah. 2c squared. Yeah, I know why I usually have the convention that c is equal to 1, but here in this term, right? In this term. Oops. So then, of course, we also need it here. Then we have it here. And then we have it here in the denominator, right? So then I guess I also have it here in the denominator. And now what? Now it becomes interesting. This was correct because I copied this from my notes. So here is the 1 over c, which I forgot on the board, but here it is present. So then the metric is probably also wrong. There's also a c squared missing here. Is that true? Or does it go away? Let me see. F prime is... No, I think it goes away, right? Or only one survives. Only one survives. One survives, yes. I have a c squared in the numerator and a c in the denominator. Okay, I think that's it. So this coordinate system was found by, this metric, I should say, was found by Paul Perlick in 1921 and by Alvar Gullstrand in 1922. These names familiar to anybody? Who has heard about Paul Perlick? Well, among physicists and even among mathematicians, he's maybe not so well known, but among historians of the 20th century, they should know him, because he was a mathematician originally, but then he went into politics. He was a statesman. He even served as prime minister in France for 2 times, I think. First during World War I, only for a few weeks, and then for a slightly longer period in the 1920s. So he was. He's better known actually for his work in politics, but he was a mathematician, and he wrote this paper on GR. And what he wrote in this paper was not that he transformed the Schwarzschild metric to other coordinates. What he wrote was, I have found a new solution to Einstein's vacuum field equation. And he wrote this down, and he saw it's a spherically symmetric solution. It has one parameter, which has something to do with the mass. And he said, of course, he knew about the Schwarzschild solution, which was already 5 years old by this time. And he said, so the Einsteinian theory is not complete. It allows 2 different solutions for one and the same problem, namely the field around a static star. And he had long discussions with Einstein, and Einstein tried to convince him that he had just found the Schwarzschild solution in new coordinates, but apparently it was somewhat difficult to convince him. Einstein gave a talk in Paris a little bit after this paper appeared, and there was a long discussion, and which was difficult for Einstein because the discussion was in French, and Einstein was not much of a linguist, but he tried his best to convince Perlick that this is no contradiction to the validity of a theory. But apparently, from what I read about this, he was not quite successful. So this was Perlick. And the other one is Gullstrand. Who knows Gullstrand? Again, he's not so well known among physicists, but among another community. In this case, it is medicine. He won the Nobel Prize for medicine, I think 1910 or something like that. So he was a Swedish, how do you say, people who, I think the word is ophthalmologist or something like that. So he studies the human eye, yeah? And he did apparently some very important work on this, which won him the Nobel Prize. And he also wrote down this metric, and he was, throughout his life, he was a fervent opponent of general relativity. And he also wrote this paper with the intention to demonstrate that this theory is stupid and that it doesn't work. And it is said that he tried his very best to block Einstein from winning the Nobel Prize. He was a Nobel Prize winner himself, so he had some influence with the Nobel Committee. And it's said that he fought against giving the Nobel Prize to Einstein with all force he could manage. But fortunately, he was not successful. As you all know, Einstein did win the Nobel Prize in 1921. So these were these 2 persons after whom these coordinates are named. So they are not exactly relativists. They are more like a little bit like outsiders. But nonetheless, the coordinate system is very useful, and we shouldn't let us be misled by the history to thinking that this would not be a very useful thing to work with these coordinates. And nowadays, of course, we understand very well what these coordinates do. So in the way we have them introduced, it's clear that now in these coordinates, if I draw a picture, maybe I can do this here. I think I don't need a big picture for this. So here I have my r coordinate, and here I have my t prime coordinate. And now I consider these sections, t bar equal constant. And if you do the same thing in the Schwarzschild coordinates, then the spatial geometry which you get, these are the so-called Flamm paraboloids. We will do this in the second worksheet. So you get something which is curved. Yeah? But if you do this here, the three-dimensional hypersurfaces, they are perfectly flat. Yeah? So if I draw a two-dimensional picture, then I have the singularity at r equals 0, of course. And apart from this is just flat space, flat Euclidean space. That's a spatial section through this geometry. Well, that the metric is indeed regular should be checked, of course. Maybe, it's not, you cannot do it in your head, I think. One has to write out a few lines. What you see immediately is that the metric coefficients do not diverge. But this has a 0 at r equal rs. And you have to check that in spite of this 0, the determinant is not 0. Yeah? So that the inverse metric will also exist. So that checks this. So the metric is regular. Is regular in the whole domain r bigger than 0. So we can use this metric for the spatial section everywhere except at the point r equals 0. So that checks this. So I just calculate the determinant of the metric now in the Perlick-Gülstan coordinates. And this would mean I have to calculate the following determinant. This is the GTT minus 1 minus rs over r. And then here you have to be careful, right? There's a 2, but this term, so to speak, comes 2 times. Yeah. So if I write down now here's a g t bar r component, then it's the thing with without the 2. So the g t bar r is c times root rs over r. Yeah, that's it. And here's the same thing, root rs over r. And the grr is 1. Here I have zeros. Here I have zeros.
Why is there a C?
I'm sorry?
Why is there a C? There's a dt, and if you write it according to the first
I forgot the c squared here. Yeah? The question is, what is x0? Yeah, does it include the c or does it not include the c? I have to make it consistently. Well, actually, usually we include the x0 into the c into the x0, then they wouldn't be there. Yeah, maybe that's better. Okay, so this thing here is the x0 squared, yeah, with the c squared. Then it's this. Okay, and here we have to now to recall what this here was. So in front of the d theta squared, I have just an r squared, and in front of the d phi squared, I have this with a factor r squared sine squared theta. And this determinant is not too difficult to calculate. This gives an r to the 4 times sine squared theta. And then I have to multiply this here, so it comes a bracket. 1 times this is minus 1 minus rs over r. And then minus this times this gives minus rs over r. And you see these two terms cancel. So this gives just a minus 1. And the whole thing is minus r to the 4 sine squared theta. Nothing bad at r equal rs. Of course, the determinant breaks down at r equal 0. We know already that there is a curvature singularity, and we have this coordinate singularity on the axis, which is just because of the use of these angle coordinates. This is a pure coordinate singularity. So this proves the statement which I've written here. The metric is regular on the domain of the whole domain r bigger than 0. And that was a proof of this. Oops. Okay, so this is one way in which you can introduce the Perlick-Gülstan coordinate, that you require that the spatial metric is flat. And now you might wish to know, what are the observers who see these flat geometry? So with which sort of observers is this geometry associated? Because of the transformation, which involves the r coordinate, yeah, t bar is t plus something depending on r, these observers will not be the static Schwarzschild observers. The static Schwarzschild observers, of course, see a curved geometry. They see the Flamm paraboloids. So what are the observers who see this geometry? And now comes the feature into the game which I've mentioned already. These coordinates are associated with freely falling particles, which come in from infinity and then fall radially towards the center. These are the observers that see this geometry. And I will try to prove this. So this will require a little bit of calculation. So we want to demonstrate that the Perlick-Gülstan coordinates are associated with infalling particles. So remember, the Eddington-Finkelstein coordinates were associated with infalling light rays. You have this light going along radial lines coming in from infinity. And actually, the structure of the metric was very similar, if you remember. Yeah? You also had a term with a differential of the time squared. Then you had a mixed term. And then you have, well, it wasn't exactly flat, but something with a certain spatial geometry. And also in this case, this factor became 0 on the horizon, but because of this off-diagonal term, the whole metric was regular. So there are many, many parallels between Eddington-Finkelstein and Perlick-Gülstan coordinates. There's also an ingoing and an outgoing version for both, right? If you had chosen the other sign here, there was one point where we have chosen a sign here. F prime was plus minus something. If you had chosen the other sign, you would have a minus sign here. And then you would not consider infalling particles, but you would consider outgoing particles. Yeah? This would obviously be associated with a white hole. So white hole spitting out particles, which are then arriving at infinity with the velocity 0. That's not extremely interesting from a physical point of view. So usually in the Perlick case, you consider the one with a sign as we have chosen it. Okay, so for this purpose, we have to calculate the trajectories of infalling particles. And it's a little bit more difficult than it was for light. For light, if it moves radial, we had only to use the property that light moves at the speed of light. This already gave us the world lines of the light uniquely because of the symmetry. Yeah, we didn't have to play around with the geodesic equation at all. The geodesic equation was satisfied automatically. Here it's different. Here we really have to use the geodesic equation in order to find out to determine particles which actually are freely falling. And so we need the geodesic equation. So freely falling particles. Hope everybody remembers. They are characterized by the following equations. First of all, well, if we parameterize them with proper time, then they have to satisfy this equation. Yeah, the curve parameter. The dot means derivative with respect to the curve parameter. And if this equation holds, then the curve parameter is proper time. And we use proper time for particles. So this means equal d by d tau. Yeah? Derivative with respect to proper time. So that's the first equation which has to be satisfied. And then we have the Lagrangian for the geodesics. Hope everybody remembers. This was g mu nu x mu dot. And the geodesic equation was the Euler-Lagrange equation. Actually, 4 components of the Euler-Lagrange equation. So this was dl by dx mu dot, and then d by d. Now I write tau, yeah, because our curve parameter is tau. When we deal with light rays, or when we do not specify what kind of geodesic we are considering, I usually write s. I reserve the letter tau for proper time, so for the particle case. Minus dl x mu is 0. So these are the equations we have to consider. So what we want to consider is for radial free fall in Perlick-Gülstrand coordinates. So let's write this equation. What is this? So I have a g t bar dot squared. Then I have a g t bar dot r dot, and I have a g r. And then comes a term with the theta dot and the phi dot, but if we are considering radial motion, then they are 0. Yeah, theta and phi are constant. So that's it. That's the first equation. And I have to read the metric coefficients from the expression up there. So this is minus 1 minus rs over r c squared t bar dot squared. Then the mixed term, 2c root rs over r t bar dot r dot, and the GRR is 1. So that's it. That's the first equation we have to solve. So what's the goal? We want to solve for t bar dot and r dot. Yeah, we want to find the trajectory. So we need 2 equations because we have 2 unknowns. Actually, the Euler-Lagrange equation gives us 4 equations. We won't need all 4 of them for this case. And actually the only one which we will need is the one where the index is 0. So where I take the derivative with respect to the time coordinate. So, so this is the first equation here. Let me write this, maybe let's call this equation 1. And equation 2 is the Euler-Lagrange equation for the case mu is equal to 0. Then I have derivative with respect to tau dl by dt bar dot minus dl by dt bar. So what is this? This is d by d tau of what? I can calculate it. Yes, maybe we can just look at this expression. We just have to remind ourselves that we have a 1/2 in front of this. Maybe I can manage to do this in my head. So the 1/2 goes away against this 2, which when I take the derivative, so I have minus 1 minus rs over r c squared t dot from the first term. From the second term, this goes away against the 1/2 in front of the Lagrangian. So I have plus c root rs over r t bar dot. No, I take derivative with respect to t bar dot, so it's r dot. And that's it. And this is 0. There's no t bar in the coefficients. So what does this mean? That means that this here is a constant of motion. Yeah? d by d tau of something is 0. Means that something is a constant of motion. And this constant of motion is usually called the energy, and it's a constant along each solution. So the second equation which we get is, cannot squeeze it up there, so I have to erase the board. The second equation is this here, that this is a constant E. Okay, so what's the second equation? The second equation is, usually one calls this minus E. Yeah? Of course, if E is a constant, minus E is also a constant, but it's just the usual convention to have this. Well, if t bar dot is positive, this means our proper time parameter along the curve goes in the same direction as the time coordinate t bar. So if we call the direction in which t bar increases the future direction, then our particle paths are parameterized in the future oriented way. And for future oriented curves, we want to have the energy positive. Yeah? And because of the minus sign here, we put a minus sign here so that E becomes positive. So the second equation is E is 1 minus Rs over R C squared T bar dot, and then minus C square root Rs over R dot. So that is equation 2. So 1 and 2 would determine r dot and t bar dot. So this would determine my path of the particles up to an initial condition if I knew E. So I have to fix the E in order to fix the path uniquely. And we want to fix the E by the initial condition for the velocity, that the particles come in from infinity with speed 0. So if we extend the world lines of the particles to t bar equal minus infinity, then they are sitting at infinity with speed 0. And then they become attracted and fall towards the center. So our initial condition, which we want to use, is, and this will determine the E. Our initial condition is that r dot for r equal infinity is 0. Let's see what we get from 1. From 1, if r is infinity, then this term is gone. So the first term is just minus c squared t bar dot squared. Minus c squared t bar dot squared, of course, at r equal infinity. This is 0, because r is in the numerator, in the denominator, and r dot is also 0 if we are at infinity. So the left, we have just this minus c squared on the right-hand side. And this implies, obviously, that t bar dot is plus or minus 1. But we want to have the parameter in the future-oriented way, so we choose the plus 1. Yeah? Of course, only at r equal infinity. So that's what we get from equation 1. And from equation 2, we get E is minus 1 c squared t bar dot at r equal infinity. And this is 0, because I have the r, 2 times. This is 0, and this is also 0. So it's 0 times 0, which is even better than 0. So this is minus c squared, because we already know that this is 1. And this implies that E is c squared, right? Why is there a minus? Why is there a minus? I think the minus is just wrong, right? There was a plus 1. Why did I write a minus here? That's nonsense. So there's a plus, and then E is c squared. Yeah. Okay. So we have determined now the E. And now we have to solve 2 equations. Let me write them again here in a box. We have to solve minus 1 minus rsr t bar dot with a c squared. Oops. Or maybe you can divide by c squared. Yes, let's divide this by minus c squared. Then it becomes nicer. So then the minus is gone. I have just t bar squared. Then minus 2 over c root rs over r t bar dot r dot plus r dot squared. I divided by c squared, right? Minus c squared. So it's minus r dot squared over c squared. On the right hand side I have a 1. So this is the first equation. That was equation 1. And equation 2 now becomes E is c squared. So I can again divide by c squared. Then I get 1 minus rs over r t dot minus r dot over c root rs over r is equal to 1. That's equation 2. So that's the system of equations I have to solve for t dot and r dot. Now let me see how I do this. There was a trick. There's a square somewhere hidden. Here's a square hidden, right? So let me write these equations again. Disclosing, discovering the square. If I take the first term, 1 times t bar dot squared extra, then the rest, what I have here is a square. So I write the first term extra, t bar dot squared, and then I got something, all terms have a minus sign, and I claim this is a square. It's a square of root rs over r, t bar dot, plus r dot over c. And on the right hand side I have a 1. You see this? Yeah? If you multiply this out, if you multiply this square out, then you get this term, and the square of this term gives the first term down there. Then the mixed term is also written there, and the last term is this here. So this is just the same as a square. And here I can isolate something very similar to what I have there. Again, I write the first term extra, t bar dot, minus root rs over r. And then let's see what I get, what I have left. This is another times the root rs over r. Times t bar dot, and minus, no, plus, because I have a minus in front of everything, plus r dot over c, and this is again 1. So this is the second version of these two equations. Now it looks already fairly good. So I have here the same expression. Wait a minute, there was a trick how to solve this. Let me check with my notes. This can be arranged in a certain way. Here I am. Oh yes. Let me just rearrange the terms a little bit. Let me put this on one side. T bar dot plus r dot over c squared. This is what? This is t bar squared dot minus 1. So that's by the binomial formula t bar dot plus 1, t bar dot minus 1. That's the first equation. And the second equation is, if I solve again for this here, t bar dot plus r dot over c. So I have this on the other side, so I have here t bar dot minus 1. So this is still equation 1, oops, and this is equation 2. And now I think I can insert equation 2 into equation 1, and then I can find the solution. Let me see, how do I do this? Yes, so now I do 2 into 1. So I leave this square, t bar dot plus r dot over c squared. And I also leave this term here, t bar dot plus 1. And for this here, I insert this expression. And this is root rs over r. Oops, root rs over r t bar dot plus r dot over c. And if I put everything to the left hand side, I can multiply, I can pull this out of the bracket, this factor. So I can write it as root rs over r t bar dot plus r dot over c, and then the rest combined together. So on the left hand side I have root rs over r t bar dot plus r dot over c, and I have taken this out of the bracket, so on the left hand side I have this with a minus sign. That means minus root rs over r t bar dot minus root rs over r. So we see these two terms cancel. And now we want to consider infalling particles. This means that this expression here, r dot over c, that this expression is smaller than 0. Yeah? Particles come from big R and move towards smaller r. So r dot should be negative. But this is also negative. Wait a minute, what is with the sign? What has happened with the sign? Yeah, it's true, it's true. This expression is negative. Here I have a minus sign, so the whole expression is negative, so it cannot be 0. Yeah, if a product is 0, then one of the two factors must be 0, but the second factor cannot be 0. Yeah? Because both terms here are negative. So this is not 0. Yeah, it's a little bit narrow here. Maybe I can squeeze here. Oops. So this is not 0. I think you cannot read it, but maybe if I just say it, it's supposed to be not 0. So this must be 0. And that's the equation we wanted to derive. So we must have that this must be 0. This means r dot over c must be root rs over r t bar dot. And if I insert this into 2, with equation 2, then I can solve for t dot. Yeah? So then I get r dot over c was, let me do it this way. Let me copy 2 and let me insert for r dot over c this expression. Then I have 1 minus rs over r t bar dot. And now comes minus r dot over c. Is that a minus sign? Yes. Minus r dot over c, and this is this here. Minus rs over 1 t bar dot. And this is 1. And this is, what has happened now? There's something wrong.
Is there like a minus missing on the first line? Dot divided by c equals to minus? Because it's 0?
Here?
Yeah. Is it minus also?
There's a minus, thank you. Yes. But I think this won't help. Then I have a plus here, but why do I have here rs over r and here's a root? So I was hoping that these two terms cancel. So what should come out is t bar dot is equal to 1, but apparently it doesn't come out. So did I miss a root somewhere, or is there a root? But this here was correct, right? No, nonsense. Here's 1 times the factor root over rs over r. And here it comes another time. So I have the root squared. Yeah? So, and then the two terms cancel. And indeed I get t bar dot is equal 1. What does that mean? What does that mean? T bar dot is equal to 1. That's a very interesting result. What does this mean for our particles? We have particles, they are parameterized with proper time. Dot means derivative with respect to proper time. And now we have found this expression. Yeah, t bar is proper time along each curve. Yeah? Our coordinate t bar has been chosen in such a way that it gives proper time along each of these infalling particles. So t bar is proper time. That's the first very important and interesting result. And of course, with this information, we now also get r dot over c is minus root rs over r. So these are the equations for infalling particles, right? They give us trajectories. So the first equation tells us that t bar is just our proper time parameter, and the second equation tells us how r changes along how r depends on tau. So it gives us the curve in the r t bar diagram. Actually, we can integrate the second equation. So if we have dr by d tau instead of d tau, I can also write dt bar, because we have verified that it is the same thing. Rs over r, we can integrate this. So then we have root r dr is minus c root rs dt bar. And I think I'm clever enough to integrate this. This would be root r to the power 3. If I differentiate this, I get a factor 3/2. I don't have a factor 3/2 here, so I have to write a 2/3 here. Then it's true, right? That's the integrated left-hand side. And on the right-hand side, I have minus c root rs. These are just constant. t bar minus an integration constant t naught, if you like. So that's the equation for our infalling particles. And that can be plotted. This can be plotted fairly easily. So here we have R. We usually plot C times t bar, that's convenient. And then, well, what is this? This is, t is coordinate on the vertical axis, so I want to have t bar as a function of R. And you see it goes with a root 3/2 with a minus sign. So apparently it's something like this. Yeah. So these are our infalling particles. These are the trajectories of our infalling particles. And somewhere here, here's our Schwarzschild radius, but nothing happens in these coordinates at the Schwarzschild radius. Yeah? So these infalling particles, they don't see anything particular if they cross the horizon here. And this coordinate, t bar, gives us proper time. Yeah? So we can, just by projecting onto this axis, we can read how proper time elapses along these curves. So these are this is the picture and the Perley-Wigglesland coordinates. And these surfaces, t bar equal constant, these surfaces, they are flat. They have flat geometry. Yeah? That's what we can read from the metric. It's still up there. There's a dr squared plus r squared d omega squared as a spatial part. And actually, what you can also show is that the world lines of these particles, these are the world lines of these infalling particles, that these world lines are perpendicular to the surfaces t bar equal constant. Doesn't look that way in the picture, but this is just a coordinate representation, right? We will check in a minute that with a metric, measured with a metric, these world lines are indeed perpendicular to these hypersurfaces. And what does this mean? It means that these are the momentary rest spaces of these observers. So they are really simultaneous events for these infalling observers. So you can imagine each of these infalling observers carrying a standard clock. So they read the standard clock parameter, which we call proper time, from their clocks. This gives us this coordinate t bar. And what is simultaneous for these observers? So these surfaces t bar equal constant, they are flat. They appear flat for them. And they are really simultaneous in the sense that these hypersurfaces, they are three-dimensional. Always remember they are the two angle coordinates, which are not shown in these pictures, right? So this is three-dimensional. There's the r running and also the theta and the phi, which is not shown. These three-dimensional hypersurfaces are perpendicular to these world lines. This is what I still have to prove. We haven't checked this. So I want to prove that these world lines intersect the surfaces t bar equal constant orthogonally. Okay, so how do we do this? So we want to prove that these world lines are perpendicular to these hypersurfaces. So obviously we need this tangent vector. Yeah, the fall velocity of these observers, let's call it u. So this would be something like, it's a vector field of course, u mu, d mu, yeah? Something like that. And then we would have to show that this is perpendicular with respect to the metric to d by dr, to d by d theta, and to d by d phi. Well, it's obvious that it is perpendicular to d by d theta and d by d phi because we don't have any cross terms in the metric. I just erased it. Yeah, the angular coordinates come only among themselves. They don't mix with the other ones. But the non-trivial statement is that this is perpendicular to d by dr, and that's what we have to show. So, fall velocity of these infalling observers or infalling particles, they are often called the Perlick observers. So what is this? So I've denoted it u, and of course it must have a t bar and an r component. And in front of this I have just the derivatives along the curves, right? What you have just calculated. So that's how this derivative is formed. Yeah? So this is, in general, I would write x mu dot, d by dx mu. Yeah, that would be the general expression. And in our case, we only have a t bar and an r component. And we can just insert what we have found. This was 1, right? We have found it as 1. So I have just dt bar. And what was the r dot? It was something negative, right? The r dot, it's up there in the box. It's minus root rs over r. And I have to take the c to the other side. So it's c times dr. That's it. So, and now we calculate, is this really true that this is perpendicular to d by dr? So we would have to prove that this is 0. Yeah? This would demonstrate, if this is 0, then this would demonstrate that these observers, the fall velocity of these observers is perpendicular to d by dr. It's obvious that this is perpendicular to d by d theta and d by d phi, yeah, because there are no d theta and d phi terms here. But this is non-trivial, so let's check this. What is u? I've just written it here. dt bar minus root rs over r c dr, and this is dr. And yeah, this is of course g t bar r. Yeah, this times this, and then minus root rs over r c grr. And what is this? I have to read this from the metric. Unfortunately, I have it erased, but I remember by heart that GTR was c times root rs over r. This was g t bar r, and this was 1. I hope everybody remembers, because we had introduced the coordinates in such a way that grr became 1. So this is minus root rs over r c. And very nicely, the two terms cancel. So this means that the hypersurfaces t bar equal constant are perpendicular or orthogonal, as you like to put it this way, orthogonal to u. And this can be interpreted as saying they are the local rest spaces. Yeah, not only the local ones actually, it's the integrated version. They are the rest spaces of the Perlick observers. So, and this completes the picture of what's going on in Perlick coordinates. Oops. And yeah, you can imagine that this is quite convenient that you have this coordinate representation. If you want to discuss, for instance, how infalling observers, how much time they spend for doing something, yeah, so the travel time for this particle from here to here or so can be directly read from the projection to the axis. So, and I think we will do at least one, maybe two little exercises with Perlick-Gülstrand. We can also, because this is proper time, it's not very difficult to calculate the redshift under which these observers are seen, right? Redshift is done in a way that you consider a proper time interval, delta tau on a world line, and you ask, you send light rays from the first event and light rays from the second event, and you ask at what proper time interval they arrive at another observer, and the quotient gives you the redshift. So because the tau is directly given by projecting onto the axis, it's again very convenient to use these coordinates. So we will do some little exercise to get more practice with these observers. Okay, and then the last coordinate system I want to discuss is a Lemaitre coordinate system, which is very closely related to the Perlick-Gülstrand coordinates. You can ask yourself the following. If you remember how the Eddington-Finkelstein coordinates were made, there we had these infalling light rays mapped onto straight lines. You can ask, here in the Perlick-Gülstrand they are curved. Here our wish was to have the proper time on the axis. And you cannot have both things simultaneously, the proper time on the axis and these curves as straight lines. But you can have something else. You can map these curves with a coordinate transformation in such a way that they become vertical. And then you can still use the proper time on the axis. And the coordinate system you get in this way, this is the Lemaitre coordinate system. So we want now to find a coordinate system where these infalling particles are mapped onto vertical lines. Well, then of course you may ask yourself, where the heck is then the singularity? The singularity is here on the left, it's the left boundary of this picture. So if these, in the new coordinates, these things go just vertical upwards, then obviously the singularity must be inclined in a certain way. And that's actually what we will do. So the singularity will then be on the angle of 45 degrees. So let's do this transformation. And this will be the last coordinate system I discuss here. That's not enough space. Oops. Let's do this here. So what was this? This was E, I think. After E, we have F. C, D, E, F, yes. So these are the Lemaitre coordinates. So, want to find transformation. And this time we start with Perlick-Gülstrand, T bar, R, theta phi. And we leave the T bar, we leave our proper time parameter as it was, but we transform the R. So we now introduce T bar, R bar, theta phi, such that our Perlick-Gülstrand observers, are at R bar equal constant. So the coordinate R bar should label the Perlick-Gülstrand observers. So we want to have a coordinate system that if we use the R bar axis here, that then these things are just vertical, that they project onto a unique R bar value. And actually we have everything on the board to find out how this transformation should be done. At least I hope that I have the expression for R. Where is it? I have it in differential form here. Let me see, how do I write this? Do I have to integrate this? I'm afraid I have to integrate this. But I have already integrated it, right? I integrated this. I have written these curves and here is it. Here it is. That's it. That's what I was looking for. That's the expression. So that's the equation which tells us how our old coordinate r changes in dependence of t bar. And now we introduce a new coordinate, which we call r bar, such that this new coordinate is constant if the t bar varies. So we can read it from this expression there. So we introduce r bar in such a way. So maybe I should solve this for r. Let me see. Okay, let me divide this just by. Let me write this in this way. What is C bar? C times T bar is, if I take this to the other side, then I have here this with a minus sign, mean minus 2/3 root r cubed divided by root rs, and then I have a constant. And this constant with a plus or a minus sign is supposed to become my r bar. That's the idea. Yeah? So I write r bar is, do I want to have it with a plus or with a minus sign? Let me check. I begin with ct bar. Okay. ct bar, then it comes to the other side, and I have plus 2/3 root r root rs, and that's it. That's my new r bar. So I read this just from this expression. Let me see, are the units correct? This is the length, this is the length. This is a length to the power 3/2 divided by a length to the power 1/2 gives again a length. Yes, seems to be all right. Fine. And if you now write the metric, if you write it out, then you get the Schwarzschild metric in Lemaitre coordinates. So I think I don't do this on the board. Gives the metric, the Schwarzschild metric. In the metric coordinates, and then we can discuss them a little bit. So the coordinates are now these here, t bar, r bar, theta, and phi. So I have to replace r in terms of r bar and t bar with the help of this equation. Yeah? I solve this for r, and then I calculate dr, and I insert this into the metric. And what I get, if I haven't messed up again, some factors, this here, minus c squared dt bar squared, plus rs divided by r. I leave the r for a moment, then I have, of course, to tell you what r is. Dr bar squared plus r squared d omega squared. And r, of course, my coordinates are t bar, r bar, and the angle coordinates, so I have to express the r in terms of these coordinates. And that comes from this equation. I solve this for r. And if I solve this for r, then I get, this is 3/2 root rs r bar minus c t bar bracket, and the whole thing to the power 2/3. So you see, r involves, of course, r bar and t bar. Yeah? So if I insert this here, if I write for r these expressions, then you see the coefficients depend not only on the radius coordinate, they also depend on the time coordinate. So the metric is no longer manifestly static. Of course it is static, it is still our good old Schwarzschild metric, but it's now written in coordinates where it's not obvious that it is static, where you cannot read this. So the surfaces t bar equal constant in these coordinates, they are time dependent. Yeah? That's the price you have to pay. But on the other hand, you get something quite nice. So let's check where's now the singularity. Singularity was r equals 0. What does this mean for r bar and t bar? If r is equal to 0, then obviously this bracket must be 0, right? So r bar minus ct bar must be 0. And where is the horizon? Oh my goodness, can I do this in my head? So this is r bar minus ct bar is what? So this is now rs. Rs to the power 3/2 and divided by this, divided by 3/2 root rs. So this is 3/2 minus 1/2 is 1, right? So that's 2rs over 3. So where are these two surfaces? Here's our coordinate system. Oh, this time I need a little bit more space to the left of the axis. So this is my r bar, this is ct bar, and my singularity is at r bar minus ct bar is 0. That's a diagonal. Yeah, this is this diagonal. Oops. Should go, should pass through the origin. So here's our singularity. Yeah, this is r equals 0. And where's the horizon? Well, the horizon is also given by a line under 45 degrees, just shifted a little bit down because of the negative sign here. So the horizon is somewhere here. This is r equal rs. And our infalling observers, they are just straight lines. Our Perlick-Gülstrand observers are just straight lines. Yeah? So you see, they come from infinity, they cross the horizon, and they end up in the singularity at the center. So it's the same picture as we have there. It is just a little bit distorted, yeah, so that the world lines become vertical. And in this case, of course, now you have to be careful. You still have these surfaces t bar equal constant here. T bar is still proper time. It has the same meaning as before, so it gives you proper time along these world lines. But these surfaces are no longer flat. Yeah, we have distorted the geometry on these surfaces, and they are not even time independent. Yeah, they depend. So the geometry depends on this hypersurface, depends on t bar. Yeah. So we have a time-dependent geometry on these three-dimensional surfaces. So that's, I would say, an obvious disadvantage of these coordinates. So for this reason, I would say that maybe the Perlick-Gülstrand coordinates are nicer, because they give you time-independent slices. Actually, this form of symmetric, where is it? Here. This form of symmetric can be found in this famous paper by Lemaitre on cosmology. Yeah, it's Lemaitre, as you probably know, was a gentleman who invented the Big Bang already in the late 20s, and then in the early 30s he wrote a famous paper on cosmology, 32 or 33, which is in French, but it is, he was Belgian. The paper is in French, but it was translated into English as one of these golden oldies in the journal General Relativity and Gravitation. So you can conveniently read it in English. And in this paper, he discussed not only cosmology, he also discussed the Schwarzschild solution. What has this to do with cosmology? Well, the reason is that the interior Schwarzschild solution, if you remember this from your first GR course, the interior Schwarzschild solution is actually a Robertson-Walker universe. Yeah? It has the same symmetries as a Robertson-Walker universe with the constant density solution. And in this context, he comes about the Schwarzschild solution, and he makes this coordinate transformation, and you find in this paper from 33, I think it is, you find a clear sentence that the singularity at r equal rs in our notation is a coordinate singularity, and that he He claims, and he correctly claims, I have demonstrated that it can transform as a ray. I think that was for the first time that this statement was in the literature, that you can transform the singularity away by a coordinate transformation. But what he did not do is, he did not explain what's actually going on at R equal Rs. So the idea that this is a horizon, this was certainly not in this paper. And that's what I meant when I said that it was only understood in the late 50s what happens at R equal Rs. So actually, if you read Lemaitre, you have the idea that everything is fine at R equal Rs. There's nothing particular happening. There's nothing, it's nothing special in this space-time at this surface. And that's definitely wrong. There is something special. Yeah, for the global structure, R equal Rs has a very important meaning. If you are trapped behind the horizon, that's an important consequence. So I should write here the year. So this was, where's the metric? So here, maybe I squeeze it here. So this was Lemaitre, Georges Lemaitre. Oops, Lemaitre, I think in 33, who introduced these coordinates. So, okay, I have 10 minutes. So actually I'm now done with the coordinate systems I wanted to discuss, and I think we will do problems in the next worksheet to the Eddington-Finkelstein, I guess, and to the Perlick-Wiggelstrand. I think these are the most important ones. And what I now want to do in the rest of this section on Schwarzschild is study again a little bit light rays and particles. I think I've heard about this already before. But I want to address some aspects which maybe you have not heard about. So when I speak about light rays, I will discuss, for instance, multiple imaging properties, that a black hole produces infinitely many images of a distant source, and that it casts what is called a shadow. Yeah? A black hole casts a shadow, and people are now very, very eagerly trying to observe the shadow of the black hole at the center of our galaxy. So there's a lot of work going on by radio astronomers who try to see this, and that's something which I want to discuss. And I will also speak again a little bit about particle motion in the Schwarzschild spacetime. So you remember what is usually discussed in first courses on GR, that if you start from the Kepler ellipses, which are a good approximation if you are far away from the source, and now you turn on a little bit the perturbations from general relativity, the first thing which happens is a perihelion precession. Yeah, that the ellipses are no longer closed, that they precess a little bit. But apart from this, they more or less keep the elliptic shape. I think that's something you know. I will not repeat it. But if you come closer to the center, if you have a particle orbiting at something like, say, 5 or 6 Schwarzschild radii, then some completely new features occur. The orbits are quite different from what you know from Newtonian dynamics. For instance, there are so-called zoom whirl orbits, where a particle goes around very fast, very often around the circle, then moves away. It's for a short period at quite a different radius, and then comes back to the one where it started and makes again a couple of turns around this. So I think you have not, most of you have not seen this before, and I want to discuss these features a little bit. Also the feature of the innermost stable circular orbit, which is quite interesting, that you cannot orbit arbitrarily close to the horizon. It's clear that you cannot orbit inside the horizon. Yeah, that's obvious, because the R coordinate must decrease. We have discussed this. So inside the horizon, you can only be in a spiral motion towards the center. That's what one calls a plunge orbit. Yeah? Because it will the plunging sound if you arrive at the center. But what is equally interesting is that you cannot orbit sufficiently arbitrarily close to the horizon. There's something which is called the innermost stable circular orbit, and there's a gap between the horizon and this innermost stable circular orbit where you actually can orbit, and that's also something I want to discuss. But I think I won't begin with this today. I will do this on next Tuesday, and I hope next week we will have quite regular lectures and exercise classes. So So for the next week, I think we have a regular program. Unfortunately, in the week after this, we will have again a problem because I will then be away. So we have to discuss what we do in the week after this. But next week, everything should be fine. So I hope you enjoy a long weekend with a May Day, and we meet again next Tuesday here in this room. See you then.